Hello, welcome to Cornell Keynotes. I'm your host, Natalie Mahwald, Chair of Cornell's Department of Earth and Atmospheric Sciences and a Senior Faculty Fellow at the Cornell Atkinson Center for Sustainability. Today we're talking about geoengineering and the science and myths of climate intervention. As concerns about climate change intensify, research around the world are exploring the potential for large-scale human intervention in the Earth's climate system, a strategy we sometimes refer to as geoengineering. One approach to cooling the Earth involves sunlight reflection methods, such as adding aerosols to the stratosphere. While still in the realm of theoretical research, such approaches raise significant scientific, political, and ethical concerns. The scientific community has assessed that it's unequivocal that anthropogenic climate change is occurring because of anthropogenic CO2 emissions. Even with recent amazing innovations in renewable energies such as solar and wind, keeping temperatures below 1.5 or 2 above pre-industrial looks really unlikely. If we act really aggressively on mitigation right now and cut our CO2 emissions, we should be able to keep temperatures below 3 degrees above pre-industrial. But there are serious dangers from these temperatures, and we need to really think about the risks of those temperatures. Scientific evidence suggests that for every rise in global mean temperature of 0.5 degrees C, which doesn't really sound that much, but every rise of 0.5 degrees, there's going to be tipping points reached in different ecosystem or different human regions. The higher the temperatures, the more tipping points we're going to see. So this raises the question of whether geoengineering is worth the risks. Joining us in the studio to talk about these considerations are two researchers focused on sunlight reflection methods. We have Doug McMartin, who's an associate professor, mechanical and aerospace engineering at Cornell, and Dan Visioni, who's an assistant professor in earth and atmospheric sciences from the College of Agriculture and Life Sciences. They're both fellows of the Atkinson Center, and together they're building a community of scholars across Cornell and beyond to equip scientists, policymakers, and society with a roadmap and thoughts for how to do a responsible evaluation of the sunlight reflection methods. So we're going to go straight into some questions and ask them more about these geoengineering methods. So first of all, can you give us a general overview of what do we mean by geoengineering and why is it even being considered here?
So the term geoengineering was originally conceived as a fairly broad set of things that includes both ideas to pull carbon dioxide out of the atmosphere and ideas to reflect sunlight. We're going to focus only on those second ones. There's broadly, so the Earth gets energy from the sun. Putting additional CO2 in the atmosphere traps some of that heat, makes it harder for it to escape. But and therefore the Earth has to warm up. If you reflect a little tiny amount of sunlight back to space, you can get back into an energy balance, so you get the same amount of energy in as out. There's a couple of different ways you can imagine doing that, and the idea that's best understood, and the idea that Dan and I spend most of our time thinking about, is you could, in principle, fly airplanes up to the stratosphere, release some material up there, and that would reflect some amount of sunlight back to space. The lower layer of the atmosphere is very turbulent. If you put stuff there, it all mixes out quickly. But there's a higher layer of the atmosphere much higher up, where if you put material there, it will stay there for a while and it will reflect sunlight back to space. That's the idea that's best understood. There's a couple of other ideas just worth mentioning in passing. The next most likely option is you can spray salt water into the right type of clouds over the ocean, and that would make those clouds more reflective. That's called marine cloud brightening. You could, in principle, reflect sunlight out in space somehow, but that's almost certainly so prohibitively expensive that it's not really, well, it's not a subject that Dan and I spend much time working on.
Okay, well, you both specialize in stratospheric aerosol injection or sunlight reflection methods. Where does this idea come from, and what tools do we have to study it, and where are we at with that? Why don't you start, Dan?
Yeah, so it's definitely not a new idea. It's something that people have been discussing actually already since the 60s. And fundamentally, the reason why it hasn't been such a new idea is because people have known that aerosols have the capacity to cool the planet for a long time. In particular, aside from observation of the fact that just aerosols everywhere in the troposphere, pollution itself helps hide some of the warming, we have in the 20th century at least 4 or 5 cases of large volcanic eruptions that through a lot of sulfate precursors, so aerosol precursors, all the way to the stratosphere, and we were able to observe that these cloud of aerosols that stayed for more than a year actually cooled the planet, actually reduced temperatures in the case of Mount Pinatubo that erupted in 1991, up to alpha degree of cooling was produced out of that for the next year and a half. So in a way, Pinatubo was one of the events that actually made these topics a lot more concrete because people were for the first time able to test climate models that were already at that time being developed and they had already been used to sort of highlight the dangers of climate change and what would happen with increased CO2 emissions. And suddenly Pinatubo gave researchers everywhere a good testing bench to understand whether we actually understood the climate system. And it turned out that climate models were pretty good at reproducing the cooling after Pinatubo. And fundamentally, that's what we do. We use the same climate models that are right now way more developed than in the 90s, these very complicated Earth system models that include representations of the ocean, the atmosphere, the land, sometimes even the ecosystems. And these are used already a lot to understand the potential risks coming out of climate change. So we use the same climate models, simulating these potential large-scale human interventions like SAI, like stratospheric aerosol injections, to understand what the impacts could be.
And I understand you have kind of a context for when you might use stratospheric aerosol injection. Doug, do you want to describe that a little bit using the slide?
Yeah. So if you bring up the slide there, nothing that we are talking about today changes the fact that you still have to cut all of your CO2 emissions. The challenge, of course, is that's hard to do. We've been talking about that for a long time. And cutting the emissions to zero doesn't actually solve climate change. Cutting emissions to zero is the point at which you've stopped making climate change worse. First thing, cut emissions aggressively. That will reduce your total amount of impacts. The next idea that is, and in fact, the only thing that in some sense is a long-term solution to climate change is to actually pull all of that CO2 back out of the air that we've been putting into it. That's referred to as CDR, for carbon dioxide removal. There's a whole pile of ideas in that space. We're not going to go into detail in them here. The challenge there is that there's nothing there that is easy. It's either expensive or it takes a lot of land to compete with, that would compete with agriculture and so forth. And so that tends to be a little bit slow. And so that's broadly the context for thinking about the solar geoengineering. I should add on top of that, we don't actually know how much the planet's going to warm if you cut emissions. And we don't know how bad the impacts will get if you, for example, manage to get to 3 degrees Celsius when we get emissions to zero. We don't quite know how bad the impacts from that will be. There's uncertainty in the policy, there's uncertainty in the technology. And so that leaves us sort of sitting at some point here thinking, well, we know climate change is going to get worse. We're not quite sure how much worse. And we do not today have a guaranteed strategy that would guarantee that we have can avoid significant climate change. So broadly, what we're talking about for solar geoengineering would be, or sunlight reflection methods, whatever you want to call it, would it make sense, and that's a question, in some sense to do a peak shaving, to basically say, for some temporary period of time, make sure that we avoid some of the worst consequences of climate change. There's a few other points that I want to make on this particular slide. One is the duration there. I deliberately left off. How long you have to do it depends on how much emissions you put in and how fast you can pull the CO2 back out. And that could be a really long time. That could easily be centuries. The second broad thing is that vertical axis on climate impacts is kind of, there's lots and lots of things that matter in the climate system. If you warm the planet by adding CO2 and you cool it back down by reflecting sunlight, you don't get back to where you started. And so you need to look much more carefully at those pathways and say, well, even if you can keep the global mean temperature cooler, what does that do to absolutely everything else in the climate system that we care about? And then the final point that I'd want to make on this slide is I've drawn it here as if it's a question of should we follow that blue path and implement geoengineering or should we not? That actually hides one of the really critical concerns that a lot of people have, which is a concern that if we did go down this path of deploying solar geoengineering, that actually might affect people's willingness to cut emissions and their willingness to pull CO2 out. That is to say that those decisions, I've drawn them as if they're distinct decisions. That's certainly the way that it has always been framed by virtually every scientific report that's ever been produced on the subject. But it's certainly plausible that other people might not view it that way, and that's sort of one of the concerns associated with deploying it.
So with this slide here, I also want to ask you, Dan, maybe to describe a little bit the context. Sometimes people refer to carbon dioxide removal as another geoengineering, and how does carbon dioxide removal, solar geoengineering, and mitigation, how do they play together here?
Yeah, so geoengineering is a term that, again, has been used to refer to CDR as well for a long time. In a way, any kind of large-scale manipulation of the climate for a specific purpose could be defined as such. And so for a lot of these carbon dioxide removal methods, especially some that have to do with changing somehow ecosystem, so whether that's BECCS, so bioenergy with carbon capture, so that's actually you have to grow specific kind of crops to draw down CO2, or even some of the methods that have to do with the ocean, right? Trying to increase the ocean sink. Those can definitely be defined as broadly climate intervention methods. So what distinguishes CDR, some forms of CDR and SRM from everything else is really the intentionality. We have been changing the climate. Humans have been changing the climate for centuries, but always as a byproduct of something else, of other decisions that were being taken. With something like geoengineering, that would be, in a way, the first time where an action is actually performed in order to deliberately change the climate and cool it, and in a way, adapt it better to our suitability. So there's really a big, huge ethical conundrum here over whether should we do this, that gets people talking a lot for sure, right? Because different people might have different sensitivities about what can we do, what should we be allowed to do. So there's fundamentally that as an ethical problem. Then there's, of course, the other problem that is different from just climate change is countries decide whether to emit or not, and other countries can't really do much to change that. But when it comes to something that is so global scale immediately, like geoengineering, there's also fundamentally a problem that is who would get to do it? What are the governance structures that would have to be put in place in order to make meaningful decisions? If we're talking about affecting Earth's temperature, who gets to decide how cool or how warm that temperature has to be? So there's a lot of also governance questions. And these, for an everyday life, these also lead to the point of, well, who would be liable? Who would be to blame if we decide to do something like this and somebody perceives that a specific weather event was caused by geoengineering? Maybe it's not true scientifically, but how do you get to the point of trust where you can convince entire populations that what's happening is good or bad?
Well, let's talk a little more about that. There's a lot of misinformation out there about geoengineering. What are your most persistent myths that you're kind of fighting against about geoengineering, or you're trying to educate people about? I don't know, Doug, if you want to start?
Well, there is certainly a small community of people who think we're already doing it. That's very definitely not true, other than, there is one company that's launching some balloons with tiny, tiny amounts of sulfur in them that doesn't actually have any significant impact on the climate system. But aside from a few things like that, nobody even has the technology today to do this at any significant scale. We don't think that it is difficult to develop that technology, but it would certainly take some years and some significant amount of funding to do it. That's probably the main misconception. I do think that there is, even within the scientific community, there's been sometimes some ideas about, what would this do to the climate system that are not necessarily always consistent with what the scientific research says. Like there's certainly been an awful lot of understandable reticence to consider this at all, and sort of a fear of it. And I think that can tend to sometimes make people overreact in some ways.
Adding 2 points to that. The first one that I would say is we would actually be able to tell pretty soon if somebody were to do something like stratospheric aerosols. Fundamentally, the stratosphere is almost entirely empty. There's almost nothing. There's just a very few particles around. Adding any significant amount, any amount that would actually affect the climate in any way, would be immediately visible to the many satellites and to the many observational systems that scientists all over the world have. Europe has multiple satellites. The US still has some for now. Japan has one, Russia, plenty of countries are observing the stratosphere for other purposes at any given time. So we would be able to tell way before somebody were actually trying to meaningfully change the climate, also because it would not be instantaneous. This is not something that you do in a day, but it's something you build up over, if you were ever to do it over a few years. But already after a few days of releasing the material, that would be already way more than it is already in the stratosphere. So we would really, if there is really no chance of a rogue actor doing this secretly and then suddenly coming up and say, hey, I've been doing this for 10 years. This is something that would be immediately visible. And that changes, in a way, the game a lot, because it means that it would be immediately under scrutiny. The other point, though, is that I feel like it merits to be said is about scale. The stratosphere is pretty empty, and so adding aerosols there would be a meaningful addition. But currently, we emit a really large amount of aerosols of pollution at any given time. The point is that we emit them in the troposphere, close to us, so they kind of immediately fall down on our head and we breathe them. But we know that they are there and that they actually do hide a little bit of the warming. So currently, humans emit 80 million tons of sulfate every year through industrial emissions, plus the Earth system emits at least as much. The point is that these aerosols only stay for a couple of days, at most a week, these sulfate aerosols, because they're soluble. And so they actually don't really stay for long, and so they don't have that much of an effect. In the stratosphere, adding a couple million tons, so a fraction, 2 or 3% of what we emit every day from the surface, would have a meaningful climate effect. But on the other hand, this is sulfate in the climate system, in the Earth system, is something that we understand pretty well because there's just so much. This would just affect where it's at and how long it stays there.
So geoengineering is really on the crux between atmospheric science and scientific understanding, ethics, as well as international relations. And even, I would say, within the fields of atmospheric science and climate science, the studying of solar radiation modification is controversial. And then also the idea of deploying is really, really controversial. I guess I often think historically about this also, having been working in climate for a long time, is at first people only wanted to talk about mitigation as a way to address climate change. Then finally now people are admitting that we have to talk about adaptation because we're already living with a certain amount of climate. And things like things like carbon dioxide removal are finally being able to be discussed. And I wonder where solar radiation modification lays in that. It's going to be in the next, for example, Intergovernmental Panel on Climate Change in a more realistic way or more substantive way. So I see some of this as an evolution of where people are at. But how do you navigate this tension between the scientific understanding of the technologies while worrying about the moral hazard and governance issues? You've already alluded a little bit to the governance issues, but maybe talk about what we're talking about by moral hazard a little bit more too.
So there's a few issues in there. One, just to be abundantly clear about it, the question of whether or not to deploy is not yet on the table. Right now, the only question is, in some sense, how much money to spend on research and what sorts of research get done, how is that research being done, who's engaged in that research, and so forth. So those are the questions right now. I guess my hope, in some sense, would be, I'm not naive enough to think that future decisions will be made purely on the basis of scientific information, but I would hope that before we get to a point where somebody says, "Oh my gosh, things are terrible, we need to consider a solution like this," that we have adequate information to be able to support that decision. So to me, I would say, regardless of all of the other issues, regardless of how concerned you are about different things, it's absolutely critical to still do the research. At the same time, one needs to make sure that when one's doing the research, it's not just, white people in the US who look like me who are doing that research, that research is being conducted by everybody on the planet, that people are able to make their own decisions about that research, that all of it is completely transparent. Dan, you've been on multiple committees talking about research governance recommendations.
Yeah, I would say, first of all, I would say that it does help to acknowledge that a lot of the concerns come from a place of care and concern, right? That, of course, the first time you hear about something like geoengineering, most people's reaction is like, wow, that's weird. That sounds crazy. And I do think that it merits to say, yes, of course, any kind of discussion about deployment right now, first of all, is not happening anywhere. And it still has to be something that's very contentious, as in, if somebody were trying to claim that we should deploy now, that those kind of claims should be under the utmost scrutiny. On the other hand, I do think that it is completely unfair to equate research with deployment, and that it is very important, as Doug said, to have as much information as possible to make sure that we can make meaningful decisions. And right now, one could say that from a purely physical point of view, looking at the results of climate models and all of the research that has been done, especially in the last 20 years, there are really good reasons to think that a very well managed, moderate deployment of SAI, instead of letting more warming happen, would reduce most climate hazards. However, that's sort of in the purely physical realm, if this is just climate researchers looking at this. There are so many more things that we need to look at, and there are so many more perspectives that need to consider, right? So when this issue gets at an international or organizational level, so when countries are talking about this, what they want to know is what it would do to my country, and how can we trust what you're saying? I think, and Paul Crutzen, who's Nobel Prize in chemistry, one of the people who discovered the ozone hole, he wrote this paper in 2006 where he said that it made sense to research SAI. But he made already this point back 20 years ago. He said the main issue with SAI is trust. How would people trust that what climate scientists say is true? And there really isn't a shortcut to trust. The only way to build trust is over time with transparency and with global engagement. And that's in a way what the community of SAI researchers and SRM researchers is trying to do. This means sharing data as publicly as possible, being clear about why we're doing what we're doing, why we're simulating the scenarios that we're simulating, and making sure the data is not just gate-kept and available to a small group of researchers who have the capacity to analyze them, but is available to the broader world. So both me and Doug collaborate with this nonprofit based in the UK called the Degrees Initiative, that makes sure that climate data and SRM results are available to researchers from all over the world, especially in developing countries. So they provide research grants to them. And we act as sort of volunteer researchers, would just help them access the data, look at the data, think about the data. But ultimately, what I've seen in my experience is that this is really the best way, or I would say the only way, to think about SRM as this global problem that can only be solved globally through engagement of everyone. And the amount of perspectives that we get just by talking to all of these researchers is really amazing, because you get to learn what do people in Kenya care about. And somebody from the Kenyan government will not come and should not come and ask me what the impacts would be in their country. They should be asking somebody from their country, some scientist from their country. So building the capacity to have these discussions happen meaningfully all over the world is really impossible to disentangle from the purely physical problem.
Great. Well, we've talked about some of the issues why you might want to do stratospheric aerosol injection. Let's talk about some of the known risks or perceived unintended consequences. And in particular, I want to highlight a question we had from a viewer, Sarah. What happens if you have to stop, for some reason it stops the injection into the stratosphere? If you want to talk about that as well as some of the other consequences. Yeah.
So I think it's useful when one's thinking about risks. I sort of divide them up into about 4 different categories. There's the broad category of, if you were doing things in a reasonably responsible way, that means that you're gradually ramping up. You're also doing lots of mitigation. You're also trying to figure out how to pull CO2 out. You're making sure that it's reasonably balanced between the 2 hemispheres. Those, you still have a set of physical uncertainties and risks that you need to understand. I think we understand a lot more about that than we did, but there's still a lot of work to be done there, sort of making sure that one follows that down to every single impact. Then there's that's in some sense much more purely on the climate science question, although there's clearly trade-offs that are human. The question that the viewer asked about termination, if you're ever doing this and you suddenly stop for some reason, then broadly over the next decade or 2, the temperatures would go back up to where they would have been without it. That is clearly a risk one needs to be concerned about. One needs to be thinking in designing governance how to make sure that you guard against that risk by, for example, having multiple people who are capable of deploying, multiple countries that are capable of deploying. And also is just yet another reason to emphasize the fact that you have to be cutting emissions. You can't just be relying on this to cool the planet. The other 2 categories, I think we've mentioned the moral hazard. That's this idea that if people perceived this as a solution to the climate problem, that would sort of relax the incentive to mitigate. Personally, I don't personally think that's a big risk, but that's probably one of the number 1 concerns that we get when we talk about this. And then the 4th category of thing I would.
And that's the moral hazard.
That's
right?
the moral hazard.
If we have this, we won't actually reduce.
Right.
We won't mitigate enough. We won't do enough carbon dioxide removal.
Yeah.
So yeah. Okay.
And I can say more about why I might think that's not such a big concern, but it is clearly a valid concern. And then the 4th category is just conflict. Dan alluded to this earlier. There is virtually nothing in the planet that every single person on the planet agrees should be done. And so I'm not, if this ever gets deployed, there will be some people on the planet who think it's a bad idea. And in the worst case, there's a drought in some country, it gets blamed for better or for worse on the deployment. Could that lead to conflict? So I think it's just critical to sort of like separate out these different categories of things, and it's very hard to articulate, well, what is the probability of some of those more societally mediated things? That depends on the governance, it depends on the trust, the extent to which the research is perceived as being legitimate, and the decisions are made with everybody's interests at heart.
And I want to thank also the viewers for adding questions. And here there's a question from Michael about the ecological impacts of this. And Dan, if you want to address
so
that.
This is one of the categories that Doug mentioned, right? And aside from everything else that is important, right, the fundamental research that has happened to now is sort of on the both climatical and now in the last 10 years also ecological potential impact. So it's useful to remember that even if done in the most perfect, idealized way possible, geoengineering would not be a magic wand. It would just not make climate change go away. It will always come with trade-offs. And the role of research and science is to try to quantify those trade-offs, not to make the decisions about which trade-offs are acceptable and which one aren't, but just to lay them out loud and say, this is what we understand, which degrees of confidence. So on the climatic side, broadly speaking, we do understand that a uniform deployment that cools the planet all in a uniform way would reduce many of the risks. We also do understand through a lot of these research that if you just cool one hemisphere, but not the other, that could have really important consequences on precipitation and weather patterns, because if you shift the balance between the hemisphere, you shift the energy fluxes, that does affect precipitation, especially in the tropical zone. So we understand how to do geoengineering badly, for sure. But even if we were to do it in the best way possible, this is, again, not a trade-off-free choice. And when it comes to aerosols, there are definitely things that we need to be at the lookout for. And so while ecological research has sort of only happened in the last 5 or 6 years now, I know a lot of colleagues, ecologists that I work with and that work independently on this topic, try to understand the potential impacts. So just to name a few, I would say things that people normally ask me about it. I would say, yes, once you put the sulfate up there, it comes back down. Now, you can say that that's a small fraction of what we put through other sources, but it will still come down. And sometimes it would come down in places that haven't seen really that much sulfate deposition in the past. So some kind of soils might be affected, and that's something where research is still sort of going on. Another thing that people are concerned of, they ask, well, if you're reducing sunlight even by a small fraction, would that affect photosynthesis? A totally fair concern, something that we're definitely working on, but in general, the broad answer to that is that, first of all, the top of the plant, what we call the top of the canopy, is not really that limited by the amount of solar radiation. There are some days where it's cloudy, some days where it isn't. They actually get way more sunlight than they need. And the bottom of the canopy, so when we're thinking about a forest, actually has not that much radiation coming and sort of in a diffuse way, so not directly. So these aerosols would change direct radiation by 2 or 3%. But they would also increase the amount of diffuse radiation because these aerosols scatter the sunlight. And so current research kind of shows that it would not have a harmful effect on photosynthesis because it would actually increase the primary productivity of most ecosystems because the diffuse radiation would go up. So there are all of these trade-offs and things that we still, again, a lot of them we still need to understand what would that do to permafrost, what would it do to air quality in very specific regions where there's already ozone production in the surface. There's still a lot of things that we need to understand deeply, but that's the whole point of research, not saying we're done, but moving on towards more understanding and expanding the circles, not just geographically, but also in terms of topics.
And of course, making sure that one's keeping those impacts in context with the things that you're benefiting, right? In terms of the ecological side, for example, you're also reducing the heat stress issues and water stress that comes with that. So it's a complicated trade-off that needs to be understood better.
So we have a question from Robert about what the composition of the aerosols would be and where that would come from. So maybe we could clarify that.
Yeah, so we normally we've talked here about sulfate. So again, sulfate is ubiquitous. It gets produced in a lot of different ways. It is actually a byproduct of a lot of different industrial processes. It's really not something that we're limited on yet, even though people point out that sulfate is also used in fertilizers and this kind of use is going up. So there's a balance there. It's interesting. But in general, sulfate is something that we know where to find, and there's a lot. Now, the reason why we talk about sulfate is because that's what's emitted by volcanoes. So again, we understand it and we have a direct proxy for it. People have also been talking, though, when it comes to stratospheric aerosols, to using different kind of aerosols, aerosols that normally don't exist in the stratosphere, like calcite or titania. The point of those would be, first of all, that we understand the chemistry so much less. They would need to be tested in the lab to understand what the impacts would be. And even if you test something in the lab, it's not necessarily true that the stratospheric air looks the same because it's so far away, different pressure, different sunlight. So for a lot of these other materials, research is still pretty much in its infancy and still needs a lot of testing. But fundamentally, sulfate is pretty much everywhere. How would you actually bring it up to the stratosphere? That's sort of another very important detail that maybe Doug can say.
Yeah, so we study sulfate because that's what volcanoes do. We know that you can have huge amounts of sulfate in the stratosphere from time to time. So that's sort of the existence proof. But then the question of how you get that, there have been a number of studies that have looked at that and pretty consistently would say aircraft are the cheapest and easiest way to do that. There's a subtlety here, which you want to get the material up into the stratosphere. In the tropics, the stratosphere, the boundary, well, that really means you want to get up to something like 20 kilometers, because you want to be not just in the stratosphere, but far enough up into it to have a reasonable lifetime. We do not have airplanes that can get to 20 kilometers, mainly because nobody's ever needed one. But if you wanted one, that would probably take you several billions of dollars to develop. It might take 5 or 10 years to develop. So that's sort of that's the default assumption that people used to be making. And more recently, I think we've paid more attention to the fact that you could start at higher latitudes. So if you were at, say, 60 degrees north, the height of the tropopause is more like 9 kilometers. And existing commercial aircraft fly up at more like 13 kilometers. That might be a little marginal, but you could certainly expect that you could start deployment with existing aircraft at higher latitudes. And it just sort of raises a little bit more of these questions of, when we are thinking about what are the impacts of doing geoengineering, of doing stratospheric aerosol injection, you have to think about, well, those impacts also depend on how you're doing it. So they, of course, depend on the material you're using, but they also depend on, are you putting this material in at high latitudes that you might want to do because you can start with existing aircraft? Are you putting it in at lower latitudes that gives you a little bit more balanced cooling? And so those things also come into play when we're evaluating impacts.
Let's start thinking more about the governance structures that might work. And we have a good question from Kat here. How would you have, some kind of international coalition with oversight? How would you think about the governance of this issue?
Go for it. Hey, this is the question, so hard.
Yeah, this I think is probably the crux of the whole thing, right? In principle, we know how to run climate models. We know how to follow that through and assess things. We, in principle, know how to make some comments about uncertainty. The governance question of how are you ultimately going to make decisions in a way that are viewed as reasonably responsible by as many people in the world as possible, that's clearly the hardest part of the whole system. I think we can certainly lay some of the groundwork for that by making sure that the research is done in a responsible way. Making sure, for example, that it isn't, Doug and Dan think this is great, but that research is looked at by lots of people, that assessment bodies like the IPCC weigh in. That will help. But I think at the end of the day, I don't know how those decisions will ultimately get made. My personal guess, and it's just a guess, would be that as long as climate change looks kind of like it does today, it's going to be really hard for people to say, I'm willing to stick my neck out and try to deploy something, despite the fact that there's going to be some opposition on the planet. So my guess is that there may be some more climate-related event that might force decisions a bit more. That's just a guess.
Yeah, I would add to these. So here's, to me, the paradox with geoengineering is that it kind of sits in a Goldilocks zone where it's hard but not impossible, and it's pretty cheap if you think about it, but its implications are huge. And I think this is relevant here because you don't necessarily need an international agreement for something like this. First of all, because there are some countries that could just go out and do it. And second of all, because it is actually unclear, I would say it's pretty clear that there are no mechanisms that are enforceable at the international level to prevent a country from releasing any kind of substance really anywhere, but especially in the stratosphere. With the Montreal Protocol being one of the very few exceptions to these, and it being very successful, but on the other hand, being very specific on the production of substances that might deplete the ozone hole, and it doesn't include sulfate. So there's a question there of who would control all of these, and do you need to get international agreement before, or will this something just will happen because a group of countries, a coalition of the willing, if you will just decide that they're better off doing it than not doing it, and every other country will just say, yep, we might complain, we might ask for some reassurances, but ultimately it does make sense. It's not the way necessarily it will go, but I do think that there's merit into thinking about the fact that overall we're not deciding right now whether to cool by 3 degrees in 100 years. We're deciding right now if it's worth shaving off half a degree or even less and avoid climate change from getting worse. And even there, this is another one of the research areas, but there's now enough research sort of on the economical, political framework around these with these kind of other kind of climate models like integrated assessment models that now have a pretty good capacity to also look at the regional impacts, essentially showing that really almost everybody would be better off by a moderate equilibrated deployment. And so, but to do that, of course, you would need access to both hemispheres. You would need some kind of assurance that nobody else is going to try to shoot down your planes. So there's a lot of also details in there. But I don't think it's totally impossible to envision a scenario in which a few countries decide to do it. At the same time, we also cannot exclude, actually at this point, it is totally also likely to imagine a scenario in which there really is a decision that is mostly driven at the civil society level to essentially say, no, we're never going to consider these, we're just going to totally ban these. Will these hold forever? Maybe not, but in the 10 to 20 years, there's many things that scientists thought they were a good idea and then haven't been applied or deployed at scale, from GMOs to some vaccines to plenty of other things. So I also wouldn't necessarily claim that I'm 100% sure this is going to happen, or it's going to happen well.
We already talked about misinformation and misperceptions about climate engineering. Tope, and I'm sorry, I'm sure I mispronounced that name, has a question about how do you address people's incorrect perceptions about climate geoengineering, kind of in a concrete way? Do you incorporate that into your research and your outreach?
So I think, well, this is hard, right? And it's hard for climate science as a whole. It's hard for any other discipline. I don't think there's as much merit in trying to debate and try to entertain debates about these things. I think that the thing that actually works is try to be, first of all, really honest and upfront. And I think and it's pretty tough, but we're doing a really good effort of making sure that everything transparent, everything up and out into the light. We're not doing anything secretly. Everybody can take a look at what we're doing. Is that enough to counter misinformation? No, but ultimately, I think the last 20 years have kind of shown that you really can't counter misinformation by just moderating discourse. And you just have to make sure that your arguments are airtight as possible, that you're willing to engage in a way that, though, doesn't give room for misinformation. That means going out, talking about this, and making sure that what you're saying actually checks out with what you're doing. To me, I know it's kind of a cop-out for this, but it's kind of the way I used to get way too upset on social media until my husband told me to stop. So now I'm like, okay, I don't argue with people on social media, but I just do my stuff.
I do think it gets better with, like international assessment reports and things like that.
That's the other one. Yes.
Like the more people are talking about this seriously and evaluating it carefully, I think that helps. It's easy for people to get stuck in an echo chamber when there isn't any information out there. Yeah. I think since you mentioned this at the beginning, that is the other important part, right? If it's me saying things or if it's a group of researchers is one thing, but the effort, climate scientists spend a lot of time doing assessments. You know it better than me. But the idea of doing global assessments where there's an agreement between a group of 20, 30, 50 people in the room
writing something down that is the best of our knowledge, and agreeing to disagree and understanding what are the points of disagreement, where we research at. I think it's really important to actually understand, to actually get to a broad point of understanding and trying to counter misinformation. And these we're starting to do for SAI in 2022, and now in 2026. In 2022, there was a ozone assessment that is mandated by the Montreal Protocols. I was one of the co-authors of this new chapter that just dealt with the potential impacts of stratospheric aerosol on the ozone layer. There will be a new one in 2026. The IPCC, the Intergovernmental Panel on Climate Change, will have almost an entire new chapter in the next working group 1 of the 7th assessment report. It will just be about SRM and CDR. The World Climate Research Program is an activity that I co-lead. There's plenty of other things. There was a meeting at the UN in Geneva in May, that now the report is out, where countries were for the first time sort of in the same room with scientists asking us questions about these. So I think there's a lot of effort going on right now to make sure that this really gets out, just of scientific papers that almost nobody reads, and actually gets to the point of, what can we say for certain? We have a climate simulator that is web-based and people can access from all over the world to start looking at the impacts that we've developed partly at Cornell, partly with other collaborations that we're very proud of. So we're trying to do a lot of effort to, get out and say our piece and show how grounded it is in scientific understanding.
Well, and just to reiterate this point, when we talk about assessments and the scientists agreeing, in addition, when we have these assessments, the governments have to agree also. So, for example, in the Intergovernmental Panel on Climate Change, every statement in there is debated by the governments as well. So they are more than just the scientists in the room,
right.
Talking about this.
Yeah.
And there is a lot more discussion happening at those levels as well than there was, say, 10 or 20 years ago.
Yep.
10 or 20 years ago, it was like 5 or 6 scientists going, this is a really interesting idea. And now it's just so much broader set of people who are engaged in that conversation and starting to think about it.
So one of the issues also can be, and that makes the governance even more complicated, is that sometimes you can have winners and losers. And we might not be able to predict those. Can you talk a little bit more, maybe Doug, you can talk a little bit more about what do we mean by winners and losers, and what are the repercussions and possibilities there?
Broadly, as I said at the beginning, if you warm the planet by adding CO2 to the atmosphere and you cool back down by reflecting sunlight, you don't get back to where you started, and you've created some sort of a novel climate. Ideally, if you perfectly compensated all of the effects of climate change, then you'd be back in a climate that we're used to and we've experienced in the past. But there may well be places on the planet that, for example, climate change made them get drier, and then you do a little bit of sunlight reflection and they get a little bit drier still. So it is possible that there are some of those places on the planet. It is, and even thinking about the range of different trade-offs that you get, if you live in an area that is currently very pristine and has never had any air pollution, now you are in fact adding a little bit of acid rain in that place that has not historically experienced it. Sorry, acid rain and air pollution aren't quite the same thing, but so even if everybody agreed on the science, you might still look and say, okay, all of these people would be better off by some metric if we were to choose to deploy, but some people might not be. I suspect that perceptions play an even bigger role than the actual science there, but that's sort of a critical thing to evaluate, and then to think about if somebody said, or some group of nations, coalition of the willing, decided, we think that we should start deploying. How do you manage the fact that there may be people who say, wait, this is going to harm us? And people have talked about different ways to bring in compensation schemes and things like that.
Well, and there's so much natural variability. I mean, everybody knows it. You have all sorts of weather events and interannual variability and everything in any location. And so how can you actually detect, was this from climate change? Was it from the Or was it just natural variability?
My honest answer would be, from looking at tons and tons of climate model simulations over the years, that most of these things that people point to and say, look, this region might be a little worse, those are in climate model simulations where we really cranked things up to a big high signal. And then we ran the model 20 times so we could get even more years to look at and say, we could tell that there's some slight difference. And of course, in the real world, you only have one world. And if let's say in 10, 15 years, people said, let's start deploying, you don't just suddenly have a huge amount of cooling. You start with a few airplanes flying up to the stratosphere. You might be cooling the planet by 1/10 of a degree after a couple of years. Maybe at the end of a decade, you might be at 1/2 a degree cooling. And the natural variability is still going to be you'll be able to see that signal in the global mean temperature. You'll be able to see that signal in maybe an Arctic sea ice, I'm not sure. But if you were going to look at an individual, the rainfall in a particular region, we don't have a good sense today of a lot of those changes from climate change. And climate change has been warming the planet by an awful lot more for an awful lot longer. So you're not realistically going to see a lot of these local impacts arising out of the signal.
So we have a question from Jay, which I think is kind of interesting, is what's the role of science fiction in popularizing or unpopularizing some of what we're talking about here?
Oh, I have so many hot takes about this.
Go for it,
I hope
Dan.
at one point Cornell will let me teach a class just about sci-fi and geoengineering.
What's the movie about the train? Don't go watch
Right,
that
so
one. Don't go watch Snowpiercer
yes.
and think you're
So
learning anything.
When we talk about geoengineering, normally the two things that people normally remember are Mr. Burns in The Simpsons that tries to hide the sun, and Snowpiercer. I really love Snowpiercer as a comic, so it's pretty nice. But it is true that past sci-fi, especially if we think about the late 90s and the 80s, has always been very skeptical about technology as a whole. And so this has been reflected in the discussion about things like geoengineering. Right now, there's a lot of emerging new literature sort of thinking through, all of the risks, sort of getting over the hangs and the anxiety about climate change and sort of really trying to explore how actually would look like. But really, I think it has an important role because through imagining futures, we can also figure out what kind of futures we want or we don't want. So now there are definitely a couple of popular pieces, popular books discussing a world in which solar geoengineering happens because maybe India is gripped by a tremendous heat wave and they decide to start. What would the future look like? Would there be a ministry for the future, looking out for future generations? So I think it's fundamental, aside from just the dry scientific papers, there's a lot that can happen just discussing and imagining different futures. And I think as we will go on, people will be more and are starting to be more and more familiar about this concept of geoengineering, so they will just balloon up. But what I think want to say on that is really, and there was a young early career scientist who gave this talk back in June, and I really liked how she said, a lot of times we get hung up on, but this will not be perfect, right? There will be winners and losers, and people only think about all of that could go wrong. I do think that there's some merit in thinking also about, but what could we do right? That maybe we haven't done before but actually works, and what is it that we could save? If we see that sea ice is going down and permafrost is thawing and suffering is happening, is there a way in which geoengineering could help? We don't know yet, but I do think that there's a lot of merit into thinking about what could we be doing by taking responsibility for our planet and maybe taking this responsibility to a new level, not by just stopping to do bad things, but also by doing maybe good things. And where could we be that is so much better than where we are now?
We have a question from Maurice about, is the appetite to research stratospheric aerosol injection increasing? And what do you think are the key things holding it back?
It's definitely increased a huge amount since I started working on this topic, which was, 15, 20 years ago that I first started paying some attention to this, at which point, you might have one NSF award active at any given point. There was essentially no government funding at all. And even private philanthropy, I think probably lots of people who followed this would know that Bill Gates put a little tiny bit of money in very early on. That was the only funding that some of us had. Now there is increased federal funding, not just in the US. The UK has federal funding as well. And there's philanthropic funding as well, going into support, for example, degrees is supported through that. Dan and I both work with an organization called Reflective that is supported by philanthropic funding. So there's appetite among people. Primarily the philanthropic sources are people who have been paying attention to climate change for a long time. They've funded renewable energy, they've maybe funded carbon dioxide removal, and they're looking at the math and saying, this isn't adding up. I think it's been a bit of a gradual shift, but I think when I started paying attention to this field a long time ago, it sounded like that's interesting, but we're going to cut our emissions and we'll stay under 1.5 degrees. That's not a problem. And I think in the intervening time, emissions have only gone up. And I think it's much more obvious to a lot more people now that we're not on a path to solve climate change by cutting emissions. And so we need to be thinking about all of the various options.
All right, well, I think that's actually a good place to end this with that note. And I wanted to thank you all very much for joining us today. And I wanted to thank Dan and Doug for their thoughts on this important topic.
And thank you for hosting us.
Thank you so much.
Thank you.